Hi guys, back for another video. Now this is a requested video and it's a series because there's just no way that I can do any justice to what it's about in one video. It'd just be too long. The subject is Transformers. We're going to discuss a lot of detail about all kinds of transformers. Power transformers, audio transformers, IF transformers, coils, chokes, and the like. We'll be getting into information dealing with cores, permeability, hysteresis curves, losses, winding ratios, impedance measurements. What's the difference between an audio transformer and a power transformer? Why is there a difference? Why is there a difference between those guys and say an IF transformer? And the like. We'll talk about ferrite cores, such as in coils it's got adjustable cores. So it's going to be a lengthy series. I'll probably do a video once. I'll try to at least get one out once a week. I can't guarantee that. A lot depends on how the rest of everything else is going, and as well as other videos and what I call priority videos. If someone asks a question either by private message or in a comment or something that they've got a radio problem or something, or I watch one of your videos and I see that you're struggling with a problem or something, then I'm going to make a video, and that's going to carry priority over any series of videos. I know I got a couple radios that were tore apart, so we'll be continued making videos on that. Plus I got some new stuff that eventually I got to make some videos of, and so forth and so on. And anyway, so we got a lot of stuff to do. So to get started today, we're going to talk about ideal transformer. And for the most part, throughout the entire series, we're going to consider transformers from the standpoint of being ideal. Now, what is an ideal transformer? Well, an ideal transformer is a transformer that has no loss. I put in a certain amount of energy, a certain amount of wattage, a certain amount of power into that transformer. I'm going to get exactly the same amount of power out. I will not lose anything. So if I put 10 watts in, I get 10 watts out. So, and the reason why we can pretty much do the entire series on ideal transformer with the idea that they're ideal is the fact that transformers for the last 60, 70, 80 years have been so darn efficient that you can pretty well treat them as ideal. They have very little loss when they're working where they're supposed to be working at what they're designed for. So they are very, very efficient, running in the upwards of 98 to 99% efficiencies. So we can actually deal with them and think of them as ideal. Alright, to start out with, we're going to talk about two different types right off the bat. We have, one is the double wound transformer, which you're probably more used to, and it can be triple wound or whatever. We're just going to deal with one primary, one secondary in this video. But most of the transformers you deal with will have a primary and a secondary. Now, I may have numerous secondaries. Like a power transformer, you can have your high tension or high voltage secondary that feeds your B+. You can have a 6.3 volt filament secondary winding, maybe a 5 volt filament secondary winding on the older transformers that use, like the 80 rectifier and some other 5U4s and some of those. They use a 5 volt. So but right now we're going to look at, but those are all separate windings, and that's what the double wound means. It's a separate winding. As opposed to the other one that I will show you is the Autotransformer. It has only one winding, yet it works as a transformer. So, right off the bat, let's look at, and before I get started, to a certain extent, some warning that we are going to deal with some math, but it's not going to be really something that you have to really worry about. The math's here more to try to help me explain to you what's going on, and I will do a very good job, or try to do a very good job of explaining the math. Most of it is not that complicated, and not, at least not early on. And so sit back, ignore the math if you want, just listen to the theory if you don't like math. If you do enjoy math, well then it's just an added bonus for you. But you really cannot do these guys justice without some math in there to explain what's going on. And if you're doing anything with a radio, trying to size up a transformer, trying, maybe you need to replace one, maybe it's an audio transformer, a power transformer, or whatever, this math will be of very importance to you. So, the double wound transformer, again, ideal. Everything's going to be ideal, so we're not going to consider in any of our math or anywhere of losses. They're not really that big, and you can pretty much, for the most part, totally ignore them. We have, for a double transformer, we have a primary winding, a core, and for right now we're going to deal with iron core or cord transformers. We have a secondary here. Now, right off the bat, the first things we're going to start talking about is some nomenclature. We'll call this, on the primary, the number of turns is N1, N for number of turns. Okay? N2 is on the secondary, number of turns, it's on the secondary. Now this, an N1 to N2 ratio is the turns ratio. So there could be like 10 turns here and 100 turns here, so it'd be 1 to 10. Step up, you can have just the reverse as a step down. But right now, being we are not establishing numbers, the primary, it's N1 for the number of turns in its winding, N2 for the number of turns in the secondary winding. We apply a voltage to the input, or the primary. We'll call that E1. If you want, you can use V1 if you're writing notes or whatever. You don't have to write notes. But E is a standard nomenclature for voltage. It stands for electromotive force. I have discussed this a little bit before, and in our video I'll discuss it a little deeper. We have a current flow. Now realize this is actually an AC circuit. Transformers only work on AC. You plug a DC into it and nothing happens. It has to have AC. So, but we gotta pick some sort of direction at some point to analyze the circuit. So when you're dealing with AC, you pick an instant in time to analyze. So at a certain instant in time, the current flow will be this way. We'll call that I1 in the primary. I for intensity or current. Same thing on the output. On my secondary, I have E2, and that's supposed to be an E. And for a current, we have I2. Okay, there's our ideal double wound transformer. And double wound only means that the two windings are completely separate from each other, so it's an isolation type transformer. Standard transformer for the most part that you've seen in most radios, or pretty much all radios. As far as like power transformers, audio transformers, IF transformers for the most part. Although there are some IF auto transformers. But double wound being that we have one winding here for the primary and one completely separate winding for the secondary. So, where's the math? Well, the math simply is this. In the math, we look at some ratios. The ratio of output voltage to input voltage is equal to the ratio of the turns of the secondary winding. Yeah, that's right. Secondary winding to the primary winding. The biggest thing I want you to realize here, I want you to notice, is that they're directly proportional to each other. E1 goes with N1, E2 goes with N2. So this goes with this, and this goes with this. So whatever ratio I put in here, whether it's like 1 to 10, 1 to 100, whatever ratio I put in here is the same that's going to be on the voltage. Exactly. So if I step up the turns ratio, in other words, for every one of these turns of primary, I have 10 turns of secondary, so I'm getting a step up. I will get the same amount of step up in an ideal transformer with my voltage. What about current? Well, current, I2 compared to I1 is equal to N1 compared to N2. It's just the opposite. If I'm running a step-up transformer, so I'm stepping up on my turns ratio, and I'm stepping up my voltage, my current steps down the same amount. So if I step up the voltage 10 times on the secondary, my current will reduce by 10 times on the secondary with respect to the primary. And there's a reason for that. The reason is, if I look at power, the amount of energy that I'm putting in, power, wattage. Wattage is E times I equals power or wattage. These two, in an ideal transformer, no losses, these two have to equal. There's no perpetual machines. I cannot create energy, so I cannot put 10 watts in and get 100 watts out. If it's 10 watts here, it's got to be 10 watts here. If it's 100 watts here, it's got to be 100 watts here. I can't create energy. So there's no free ride. So if I up my voltage, I have to lower my current to keep the wattage the same. That's your typical double wound ideal transformer. Real basic math for it. The biggest thing I want you to realize is whatever your turns ratio is, it's equivalent and it equals to the voltage ratio. So if it steps up in the turns, it steps up in the voltage, but it steps down in the current, same amount. Now what about an auto transformer? Well, let's look at one. Let's see, we got a deal here, this goes all the way through to here. Come up here. And this guy comes here. This is N1, and this whole thing is N2. E1 again, and E2. again. I1 and I2. Single winding, non-isolation. This basically is, an autotransformer is really what your variac is. The only difference between something like I drew here and a variac is on a variac I can put a little arrow here because I'm adjusting this. This can move up and down. And that's what you're doing when you turn the knob on a variac. But it's nothing but an autotransformer. That's how come with most variacs you can plug in 120 volts in them and you can probably squeeze, you know, depending on the variac, 130, 140 volts out of it if you crank all the way up, because it's stepping up at that point. You move it far enough, it turns into a step up. Otherwise it's a step down transformer. But it's an auto transformer. No different other than the fact instead of being stationary, you can actually move this tap back and forth to get your different voltages. But as far as ratios go, it's exactly the same. E2 to E1 equals N2 to N1. I2 to I1 equals N1 to N2. Same thing as the double wound. No difference. The only difference is basically all I've got is just a winding and going over the entire secondary, that entire winding is my secondary, and I got E2 or my output there, and then I tap it for my primary. It's the only difference, as opposed to the double wound where I have two separate coils. The biggest thing about these that I want you to really truly pay attention to, unlike the double wound, which is fully isolated, the only connection between the two windings is the mutual inductance. In other words, as the magnetic field builds up on one side, it cuts and creates a voltage in the secondary, and as it collapses it keeps doing that. So the biggest thing is it's fully isolated electrically, other than mutual magnetism there, inductance, whereas this is a solid connection. There's no isolation. This lead goes straight through, this lead is hooked in here and going through around. So there's no isolation. So your variac, just a plain Jane variac, is not an isolation transformer. Other than that, they work the same. And basically all it's doing is it's building a magnetic field here in this winding, and we'll go over deeper about how transformers truly work. Right now we're just doing an introduction. But basically what it's doing is build a magnetic field here that encompasses the entire the entire winding on the secondary. And that's how it's doing that. And it just deals with the number of turns difference between these two. Same turns ratio though. Same style turns ratio. You can have step up, step down. Like I say, the variac pretty much most of the time works as a step down, but once you get past 100%, it'll actually start stepping up your voltage. Okay, where are we at? Oh boy. I think I'm going to cut it off right here. I had more stuff to do, but the others are going to be a lot more explanation to them. So I'm going to stop this. I know it's a little bit shorter than my usual videos, but I do got another video I want to get up today. We're kind of taking a break right now because right now we're dealing with heat indexes around 115, 120, and there's still no heating or air conditioning at the apartment, so no air. It gets pretty warm. So we have humidity levels, dew point levels approaching 80, and it's like 95 out. So we're taking a break and not really working that hard. So I thought I'd go ahead and try to squeeze out a couple videos for you guys and stuff. Tomorrow I go back to work on the remodel because tomorrow there's a cold front going through tonight and it's supposed to be a lot nicer. So anyway, until the next time, thanks for watching, and I look forward to your comments and stuff. I'll try to answer a few and try to stay on top of this stuff. So see you on the next video.